Chemical composition. So in this chapter, we'll try to understand a very important unit that is very commonly used in chemistry. So these are some of the units that are used to quantify and understand the composition of substance. It's very commonly used. It will be used throughout the chemistry course if you're going to be working in chemistry, in the field of chemistry or biochemistry. And that unit is moles. So it's not very different. It's not a very difficult unit to understand. Before we understand moles, let's talk about some unit, very similar unit that is commonly used in our everyday life. For example, a dozen. When I say you have 1 dozen eggs, what does that mean? That simply means you have 12 eggs. What is this dozen? This dozen essentially is one of the units that is used to represent a certain number of items. 1 dozen is always 12 units. So if you have a dozen eggs, you have 12 eggs. If you have a dozen apples, you have 12 apples. If you have 2 dozen oranges, then you have 24 oranges. So dozen basically is representing a certain number of items. That's exactly what mole is. In chemistry, we know we are working with atoms, molecules that are really small in size. So if we talk about how many atoms are present in a certain substance or how many molecules are present in a substance, then dozen will really not work well for us because we will have multiple millions and billions and trillions of atoms and molecules because they are so small in size. So that is why we use the unit mole. What is 1 mole? 1 mole simply represents 6.02 times 10 raised to power 23 units. 1 dozen of anything is these many units of that. So if you have 1 mole of anything is these many units. So if you have 1 mole eggs, that essentially means you have 6.02 times 10 raised to the power 23 eggs. If you have 1 mole of apples, you have these many apples. What is important here is, remember, when I say 1 mole of something, you have these many of that thing. Okay, so if I say you have 1 mole of atoms, that means you have 6.02 times 10 raised to power 23 atoms. If you have 1 mole of molecule, then you have 6.02 times 10 raised to power 23 molecules. Okay, so what is important to remember and understand is that when we say 1 mole of a substance, then you have these many of that particular substance. Okay, just how if I say you have 1 dozen eggs, you would not say that you have 12 apples. You have to have the same number of eggs. Similarly, if you're working with mole of atom, you need that many atoms. If you have mole of molecule, it means you have that many molecules. How do we use this number? This number right here is called as Avogadro number. Okay, Avogadro, why? Because he came up with this number, so this is called as Avogadro number. Avogadro's number 6.02 times 10 raised to power 23 items. What you need to remember is that this right here is a conversion factor for you. It is a conversion factor to go between moles and number of units. Now that unit could be atom, it could be molecules, it could be particles, ions, it depends on what we are working with. If I'm working with atoms, then I have these many atoms. How will we use this number? Remember, this number will be used as a conversion factor. Like you see here, these many particles, that could be atom, molecule, ion, whatever. How would you use this? Remember, when we have a conversion factor, we use it like a fraction, like this, where one of these quantities has to go in the numerator, the other one goes in denominator. And if you remember from dimensional analysis, you would know that the way to figure out which of these factors we use depends on what is your starting unit. Okay, so what is important here to remember is that 1 mole is related to number of particles using this number. Okay, so let's try some questions based on this. So for example, the number of atoms in 2.0 moles of aluminum is what? Okay, what's given to us is moles. So we'll go back to our approach of dimensional analysis. What is given to us is 2 moles of aluminum. So I have moles of aluminum. The question is asking how many atoms of aluminum do you have? Moles are given to me for aluminum. The question is asking atoms. What is aluminum? Aluminum is an atom in itself, right? Which means, for example, if I say you have 2 moles of eggs, then you would get that many eggs. So aluminum is an atom, which means it's related to number of atoms. What is the conversion factor that relates these two quantities? 1 mole is 6.02 times 10 raised to power 23 atoms. Okay, so you start now with what's given to you, which is 2.0 moles. We will multiply it with a conversion factor that comes from this. One of these go in numerator, one goes in denominator. How do I decide it? That depends on what is my starting unit. My starting unit here is moles, which means moles goes in the denominator. How many moles? 1. How many atoms? 6.02 times 10 raised to power 23 atoms. Mole cancelled. You're left with number of atoms of aluminum. That's exactly what I needed. Plug this into your calculator. It will give you the answer, which is 1.2 times 10 raised to power 23 atoms. I started with how many sig figs here? 1, 2. So my answer should have 2 sig figs, which is 1.2. So the answer here is C. Let's try another question. The number of moles of sulfur in these many atoms of sulfur. So what is given to us in question is atoms of sulfur. The question is asking how many moles of sulfur are present. As long as you have this, you're talking about the same substance, you're good. This is sulfur, this is also sulfur. As long as it's the same substance, moles and atoms can be related directly to each other by using 1 mole is 6.02 times 10 raised to power 23 atoms. And why did I decide atoms? Because sulfur is an atom. So that is why when I say I have 1 mole of sulfur, I'm talking about atoms of sulfur. Now you start with what's given, which is atoms. 1.8 times 10 raised to power 24 atoms. You will multiply it with a conversion factor, a fraction that comes from this conversion factor. My starting unit now is atoms, which means who should go in the bottom here? That should be same as atoms. So I'll put atoms right here. How many atoms from my conversion factor? It's this many, which is 6.02 times 10 raised to power 23. And 1 mole of sulfur goes on top. Atoms and atoms cancelled. You have mole of sulfur. When you plug this into your calculator, one important thing to remember is make sure you understand how to plug in these exponents into your calculator, first thing. Second thing, if you're dividing by the exponent, when you plug this into your calculator, please make sure you put this in parentheses. Okay, so what you want to plug into your calculator is 1.8 times 10 raised to power 24 divided by, multiplied by 1, which is same number, divided by this number. But put this number in parentheses, 6.02 times 10 raised to power 23, and then hit the answer key. Why? Because your calculator, if you do not include parentheses, it will first multiply by 6.02, divide by 6.02, and then it would multiply it by 10 raised to power 23 instead of dividing by the whole thing. So please make sure if you're using these exponents in multiplication or division, one suggestion is to include them in parentheses. Okay, if you plug this into calculator, the correct answer should be 3.0 times 10, 3.0 moles 3.0 moles of sulfur. How my starting, this has 2 sig figs, so my final answer should have 2 sig figs because this is multiplication. Okay, moving on. This was when we were talking about moles of atoms. Similarly, when we talk about a molecule, if I say you have 1 mole of water, what does that mean? H2O is water. H2O is not an atom, it is a molecule. How do you know? If any substance has more than one atom, then it is now a molecule. Okay, so when I say 1 mole of water, that means I have 1 mole of molecules of water, which means I have 6.02 times 10 raised to power 23 molecules of water. Okay, so make sure you understand the difference here. Which one is atom, which one is molecule? If I say 1 mole of hydrogen, H, then I have 6.02 times 10 raised to power 23 atoms of hydrogen. Why? Because when I say H, H is an atom by itself. It's by its own. Okay. If I say I have 1 mole of H2, which is hydrogen gas. Now, because I have more than one atom, I can simply call it a molecule. I would have 6.02 times 10 raised to power 23 molecules of H2. So that is the difference when it comes to atoms and molecules. The number stays the same. The difference is what you're starting with. If you're starting with a molecule, you will end with molecule. If you're starting with atom, you will end with atom. So, for example, another thing I would like to mention here is, for example, if I have 1 mole of aspirin, aspirin is this, C9H8O4, meaning it has 9 atoms of carbon, 8 atoms of hydrogen, 4 atoms of oxygen. So if I have 1 mole of this, that simply means I have 6.02 times 10 raised to power 23 of these. And what is this? This is a molecule. So I have these many molecules of C9H8O4. Okay, now what if I'm interested in how many carbon atoms does this have? How can you relate that? Remember, when you see these subscripts tell you how many atoms are present. So in this compound, I have 9 atoms of carbon. I have 8 atoms of hydrogen, 4 atoms of oxygen. If you have 1 molecule of this, you have these many atoms. If you have 1 mole of this, if you have 1 mole of C9H8O4, you have 9 moles of carbon. If you have 1 mole of this, you have 8 moles of hydrogen and 4 moles of oxygen. So that's basically how you can get number of atoms from a molecule. So meaning, if I have 1 mole of H2O, how many hydrogen do I have there? I have 2 moles of hydrogen here. This subscript is basically telling you how many atoms are present in one molecule, or how many moles are present in 1 mole. If I have 1 mole of oxygen, oh, H2O, sorry. If I have 1 mole of H2O, I have how many moles of oxygen? 1 mole of oxygen. If a number is written as a subscript, that is your number of moles of that. If no number is written, that simply means it's a 1. So for example, if I have 1 mole of CuSO4, then it consists of 1 mole of copper, 1 mole of sulfur, and 4 moles of oxygen. Okay, I'm writing this as equal. Equal doesn't mean that they are equal to each other. It simply is like one way of representing that if you have 1 mole of this, then you have 4 moles of oxygen in that sample. Okay. All right, so we'll try some questions based on this idea. Again, what are these? These are your conversion factors. So for example, the question is asking how many atoms of oxygen are in 0.150 moles of aspirin. So what's given to me is, let's write down what's given, is moles of C9H8O4. And the question is asking how many atoms of carbon are present here. Sorry, oxygen. How many atoms of oxygen? Now, first thing you should notice is this is different. Moles are given of one substance, atoms are of the other substance. So you cannot relate these two substances unless you have a relationship relating them. Okay, there's no direct relationship between them. Only way you can relate them directly is through moles. If I know moles of this, I can figure out moles at number of molecules of this, but I cannot get to atoms of this, right? If I need atoms of oxygen, only relationship you need between the number of atoms or number of particles is 1 mole of a certain substance has 6.02 times 10 raised to power 23 atoms or molecules of that substance, which means I need to use this, okay? Because there's no other way to get to number of atoms. So if I want number of atoms, what should be my other unit relating it? That should be moles. So if I want atoms of oxygen, I need moles of oxygen, which means I need one midpoint here. First, I'll have to find mole of oxygen. When I have that, I can convert it to atoms of oxygen. Now, is this relationship? I know. This is 1 mole of oxygen has 6.02 times 10 raised to power 23 atoms of oxygen. What about this though? I need a relationship between moles of this and moles of this. 1 mole of C9H8O4 is, it has how many moles of oxygen? 4 moles of oxygen. So I can use this to convert moles of molecule into moles of oxygen, and then I can use this Avogadro number to go to atoms. Okay, so now we start with what's given, which is 0.150 moles of C9H8O4. I will multiply it with a fraction that comes from my first conversion factor, which is this. So one of these has to go in the bottom and one goes in the top of my fraction. How do I decide that? That depends on what is my starting unit. My starting unit here is mole of C9H8, which means what goes in the denominator is mole of C9H8O4. The same unit should go in the crisscross direction. Where is it? It's right here. How many? 1 mole, and whatever's left goes on the numerator. So 4 moles of oxygen. Mole and mole gone. I'm left with moles of oxygen. Next, I have moles of oxygen right here, which means now I'm going to the next step, which uses this conversion factor. Again, one of these goes in numerator, one goes in denominator. How do I decide? Based on my starting unit. My starting unit is now moles of oxygen, which means I should have the same unit right across here. Moles of oxygen, so moles of oxygen goes here. How many moles of oxygen? Right here, 1. The rest goes on top. Mole of oxygen cancelled. I'm left with atoms of oxygen. So if you plug 0.150 multiplied by 4 multiplied by this number and divided by 1, it will give you your final answer. And the final answer that I have is, my calculator gives me 3.6132 atoms. Oh, I am missing my exponent. Times 10 raised to power 23 atoms of oxygen. Now I decide how many sig figs do I want. This has 1, 2, 3 sig figs. This in the middle, we don't care about sig figs because it's a fixed number. This is also a fixed number, so we don't care about sig figs. How many sig figs do I finally want is 3. So 1, 2, 3. My number should end here, which will give me 3.61 times 10 raised to power 23 atoms of oxygen. Okay, let's try another question, similar example, but we'll not go through all of this in this slide. How many moles of each element are in 0.5 moles of this? Okay, how many moles of each element? So some of this, you might be able to do this in your head now. What does this mean? If you have 1 mole of Fe3PO4 whole twice, that means how many moles of iron do I have here? You look at the subscript. How many iron atoms are present? 3. Okay, which means for every 1 mole you have 3 of these. So for every 0.5 you would have half of this, right? 1 has 3, so 0.5 would have based on that. Or you can start the way we usually do using conversion factor, 0.50 moles of Fe3PO4, multiply it with this factor, moles of Fe3PO4 goes in the bottom and this goes on top, which means you have half of 0.5 multiplied by 3, which will give you 1.5 moles of Fe. This was 2 sig figs, so this is 2 sig figs. Okay. Similarly, it's asking of each element, so I can do phosphorus. Now you might be able to do this in your head, or you can use this longer approach. It doesn't matter. Now I'm interested in phosphorus. Based on this chemical formula, remember, how do we find number of atoms? Whatever is your subscript is multiplied by this number. Okay, you don't add them, you multiply them. So if I have Fe3PO4 whole twice, how many phosphorus do I see here? 1 multiplied by 2. So how many P are present here? 2 P's. Okay, which means I can simply say for every 1 mole of this, you have 2 moles of P. So every one has 2, so every 0.5 will have half. So 2 multiplied by 0.5, that would give you 1 mole of P. So that would be your answer. Okay, or let me say that's your answer. If I'm interested in oxygen, for every 1 mole of Fe3PO4 whole twice, I have how many oxygen? Subscripts get multiplied. So 4 multiplied by 2 will give you 8 moles of oxygen, which means if you have 0.5, you have 4 moles of oxygen. So that's your answer for oxygen. Okay, and if you want, you can also do it this way, where you use these conversion factors and you do start from your starting number and use the conversion factor. Okay, still give you the same answer. Okay, the next concept is molar mass. So when we say amount of substance, we now understand 1 mole has how many units of it. Similarly, if I'm interested in the mass of that substance, mass of 1 mole of any substance is called as its molar mass in grams. Okay, so remember this. What is molar mass? Molar mass is mass of 1 mole of a substance. So if you're interested in how many grams of substance do you have, you will have to use this conversion factor. 1 mole is going to weigh how much? It will weigh equal to its molar mass in grams. Where do you find the molar mass? The number that is written in the bottom of the under the element in periodic table, that gives you the molar mass of that substance in grams. So which means if you have 1 mole of sodium, sodium is an atom, so if you have 1 mole of sodium atoms, how much would they weigh? They will weigh 22.99 grams. Okay, so using this, you can find molar mass of the substance. Example, 1 mole of silver would weigh 107.9 grams, 1 mole of carbon would weigh 12.01 grams, 1 mole of sulfur would weigh 32.07 grams. So now if you try to understand this, 1 mole of silver has how many atoms of silver? 6.02 times 10 raised to power 23. Similarly, if you have 1 mole of carbon, how many atoms do I have? 12.01. Oh, sorry, that is molar mass. How many atoms do I have? 6.02 times 10 raised to power 23 atoms of carbon. If I have 1 mole of sulfur, how many atoms do I have? 6.02 times 10 raised to power 23 atoms of sulfur. Okay, but how much do these each weigh? 1 mole of silver weighs 107.9 grams. 1 mole of carbon weighs 12.01 grams. 1 mole of sulfur will weigh 32.07 grams. Why? Because these are the numbers given to you right here. Okay, even though they have same number of atoms, each of them weigh separate or weigh different. Why? just simply because each atom of silver weighs different. Okay, for example, if you think of like 1 dozen, if you have 1 dozen apples, if I say 1 dozen grapes, you have 1 dozen grapes and you have 1 dozen apples, big apples. Okay, how many grapes do you have? You have 12 grapes. How many apples do you have? You have 12 apples, right? But who is going to weigh more? Apples will weigh more than the grapes. Even though you have the same number, they have different grams, different mass. Why? Because each grape weighs different from each apple. That's exactly what this is. When you have 1 mole of all of these, they have same number of atoms, but they have different grams because each atom here weighs different. Okay, that is how, so make sure you understand this difference. Okay, so this is molar mass. So this is molar mass of a element or an atom. Okay, this kind of shows you the same example. So if you have hydrogen, carbon, oxygen, sulfur, calcium, chlorine, copper, these are all atoms of the substance. So you have same number of atoms, but they will all weigh different. They look different. For example, 1 mole of sulfur is 32 grams. It looks like this. 1 mole of carbon is 12 grams. Looks like this. Even though they have same number of atoms, they look different. They have different mass. Why? Because each unit in there has a different mass, a different number of atoms. Okay. All right. Now this was mass, molar mass of one substance, one element. What if I ask you molar mass of a compound? How would you find that? So if you're interested in molar mass of a compound, like water, how do we do this? What is molar mass of water going to be? Molar mass of water is going to basically be sum of all the atoms in the compound. What atoms does it have? It has 2 hydrogen atoms and it has 1 oxygen. Nothing is written, that means one oxygen atom. So you take mass of all of these. How many hydrogen? How much does each hydrogen weigh? It weighs this, the number that's written right here. Each hydrogen weighs 1.008. So 2 hydrogen atoms would weigh twice of that. So 2 multiply by that. Plus each oxygen weighs this, which is 16.00 grams. So this is when you add all the masses of atoms together, that will give you mass of molar mass of water. This is molar mass of water. And again, molar mass is what? Molar mass is mass of 1 mole of water, which means this is now your conversion factor that you have. If you have moles of water, you can figure out its gram by using this conversion factor. So this is new conversion factor that's given to you now. Okay, remember mole is same. If you're interested in grams, you can find it by using molar mass. Another example we can try is, for example, this: calculate molar mass of lithium carbonate used to treat bipolar disorder. So lithium carbonate is this compound. If I need molar mass of this, how many lithium atoms do I have here? I have 2 lithium, plus I have 1 carbon, and we have 3 oxygen. Okay, whatever your subscripts are, they give you number of atoms. If you have like something multiply in the parentheses outside, multiply the subscripts. So now I just add the mass. 2 lithium means 2 times 6.94, that's the mass of lithium. 1 carbon is 12.01 plus 3 oxygen, each oxygen is 16.00. You add it all together and take the sum, and that would give you mass of molar mass of lithium carbonate, which is 73.89 grams. So what is your conversion factor here? It simply means you have 1 mole is 73.89 grams of Li2CO3. So that is your conversion factor to go between moles and grams of that substance. Okay, now because this is mass, molar mass is mass of 1 mole of a substance, sometimes the unit is also written as 73.89 grams per mole. Per mole means mass of 1 mole of a substance, right? So if I say what is molar mass, of Li2CO3, it is going to be 73.89 grams per mole. This is also a very commonly used unit. When I say gram per mole, that means I'm talking about mass of 1 mole of that substance. Okay, so that is molar mass. That's how you find molar mass. Okay, how can we use this? This is again a conversion factor for you. So if you need to go between moles and grams, you have a conversion factor now. Here, what is molar mass of methane? CH4. CH4 has 1 carbon, so 12.01. 1 carbon, 4 hydrogen, so 4 times 1.01 or 0.8 from your periodic table will give you a total of 16.05 grams. So now you can say 1 mole of CH4 is these many grams of CH4. This is a conversion factor. Again, one goes on top, one goes in the denominator. Now what is important here is you are basically building a map. Okay, so you need to remember map that you use for a lot of your questions. Okay, so this map, let's try and understand it. You'll have to memorize this. So if you have moles of an element given to you, you can relate it to grams of that particular element. How? Using molar mass, which means 1 mole of that substance is going to be equal to molar mass in grams. This is my conversion factor to go between grams and moles. Similarly, if you want to figure out how many atoms are present in that element, you can use the number which is Avogadro number, which would be what? 1 mole is 6.02 times 10 raised to power 23 units. Atoms, ions, particles, whatever is needed. So these are your conversion factors. How will you use these? Dimensional analysis. Similarly, if let's say you're given moles of compound, instead of element you have a compound given to you, how is it related to grams? Again, using molar mass. 1 mole equal molar mass. How is it related to number of formula units or molecules? 1 mole is 6.02. So this is same. What changes is if you're given moles of compound and the question is asking what is the moles of element, the conversion factor here is going to be your formula subscript, which means 1 mole of the compound will be equal to the subscript mole of atoms of that particular element. Okay, so this gives you the moles of that element. And if you have moles and you want to find grams, you can go this way, or you want atoms, you can go this way. So basically this is like a map that tells you which direction you need to go, how your solution map would look like. So if grams of element are given to me and the question is asking how many atoms do I have, first thing I'll have to do is I'll have to go from grams to moles, then moles to atoms. Okay, so this is basically just a map to help you figure out what step to use. For example, if grams of compound are given to me and question is asking how many grams of a particular element is present, I cannot go directly from here to here. There is no way that I can go directly here because I don't have a relationship. The only way I can do this is I'll have to convert grams of compound into moles of compound first. Then I'll convert moles of compound into moles of element, and then I can convert moles of element into grams of element. So this is basically giving you, it's like a cheat sheet to help you figure out which direction and what numbers or what information you need to use to get your final answer. Okay, so let's try some questions based on these. Example, calculate the moles of sulfur in 57.8 grams of sulfur. So let's write down what's given to us as grams of sulfur. And the question is asking how many moles of sulfur are present. Do I have a relationship between grams of sulfur and moles of sulfur? The answer is yes, which is molar mass. So go back to your map and you'll find 1 mole of substance is equal to molar mass of that particular substance in grams. Okay, the substance I am interested in is sulfur, which means I need molar mass of sulfur. What is molar mass of sulfur? If you look up in the periodic table, the molar mass of sulfur is 32.0 grams, which means what would be my number here? 1 mole of sulfur is going to be 32.00 grams. And that's it. Now you have your map completed. Start with what's given, 57.8 grams. Multiply it with the conversion factor to get rid of grams of sulfur. I will put grams of sulfur here. How many grams of sulfur? Right here, 32. And 1 mole of sulfur goes on top. Gram gone. I'm left with moles of sulfur. So you just plug this into your calculator, which would be 57.8 divided by 32.07. This is 3 sig figs. So this is 4 sig figs. So I want my final answer in 3 sig figs, which would be 1.80 moles of sulfur. Let's try another question based on very similar example. How many copper atoms are in 3.10 grams of copper penny? So what's given to me is grams of copper. Question says you have 3.10 grams of copper. It's asking me how many atoms of copper are present. Now if you go back to your map, you'll see if you have grams of element, copper is what? It's an element by itself, it's an atom. And the question is asking how many atoms. I do not have a direct way to go from this to this. The only way I can convert grams to copper atoms is I need a mid step in between, which would be moles of copper. So first I'll have to convert grams to moles, then I can go from moles to atoms. What is the relationship between grams and moles? Molar mass. So 1 mole of copper weighs how many grams of copper? That you can get from periodic table. Periodic table tells me the molar mass is 63.55 grams. Next, I go from moles to atoms. What is the relationship between mole and atom? Avogadro number, which means 1 mole of copper is 6.02 times 10 raised to power 23 atoms of copper. And that's it. Your map is complete. Now you start with what's given, which is 3.10 grams of copper. I will multiply it with a conversion factor that comes from the first factor. That comes from the first factor right here. One of these goes in top, one goes in bottom. This is grams of copper, which means what I need here is same. I need grams of copper, which comes from here. How many grams? 63.55 grams. And who goes on top is the other unit, 1 mole copper. Gram gone. I have moles of copper, which is this, which means I have figured it out. Next, I need to go through my second step here. I multiply it with another factor that comes from here. My starting is moles of copper, so I should put moles of copper in the bottom. How many moles? Right here it says 1, so 1 mole copper, and the other information goes on in the numerator, atoms of copper. I put atom. Why? Because this is an atom. Mole of copper gone. I have finally unit is atoms of copper. So if you plug this into your calculator, it should give you the right answer. What will you plug in? 3.10 multiply by 1 multiply by 6.02 times 10 raised to power 23. Get your answer, then divide it by 63.55. Okay. Now again, this is 3 sig figs. This is 4 sig figs. This is a counted number, so I don't care. So least answer should be 3 sig figs. So if you plug this in, you should get 2.94 times 10 raised to power 22 atoms of copper. Table salt NaCl weighs about 0.30 milligrams. How many moles of NaCl is this? So what's given to us is milligrams of NaCl, and the question is asking find moles of NaCl. How will I find moles? Remember, if grams are given to you, you can relate it to moles by using molar mass, because my molar mass is in grams, but what's given to me is milligrams, which means I'll have to first convert my milligrams to grams of NaCl. Then I can convert grams to moles. What is the conversion factor here? 1 milligram is 10 raised to power minus 3 grams. What is the conversion factor for the second step? Molar mass. 1 mole of NaCl is equal to molar mass in grams, which means I need to find the molar mass. It's a compound. So let's do that separately. NaCl has one Na and one Cl. One Na weighs 23.00, one Cl weighs 35.45. When you add it up together, it will give you 58.45 grams, which means this is 58.45 grams. Now you have your map done, so just set this up and get your answer. Start with this 0.3 milligrams, multiply it with a factor that comes from here. My starting unit is milligrams, so what goes in the bottom is milligrams. Oops, milligrams. How many milligram? Right here, 1, and the other unit goes on top. Milligram, milligram gone. Now I multiply it with another factor that comes from this. Grams, my starting unit now is grams, so who goes in the bottom is grams. How many grams? This right here, 58.45 grams. And who goes on top? 1 mole of NaCl. Gram, gram cancelled. Your final answer is mole of NaCl. Okay, plug this into your calculator and the answer it should give you is 5.1 times 10 raised to power minus 6 moles of NaCl. Okay, now in this case this was 2 sig figs, that is why my final answer is 2 sig figs. You could get this, or if you write this, that both are same, 0.1, 2, 3, 4, 5 and 6. If you give me this, that is also okay. 1, 2, 3, 4, 5, 6. Either one is okay, as long as they both have 2 sig figs. Any of these answers would be regarded as correct. Okay, let's continue then. The last question that we try. If a 750 gram sample of dry ice sublimates to CO2 gas, how many CO2 molecules are released into air? So what's given to us is you have grams of CO2. This is solid CO2. The question is asking once it turns into gas, how many molecules of CO2 are present? So basically it's gas or liquid or solid. It doesn't matter. What matters is what's given to us is grams of CO2. What I need is molecules of CO2. So how would I go from grams to molecules? This is a molecule CO2, but I know there's no direct way to do this. So if I want to go from grams to molecules, I will have to take a stop in the middle, which is going to be moles of CO2. I can convert grams to moles first and then moles to molecules. The conversion factor to relate grams and moles is molar mass. So we have to find molar mass of CO2. 1 carbon, 2 oxygens. So each carbon is 12.01 and each oxygen is 16.00. When you plug this in, this would give you molar mass of CO2, which comes out to 44.01 grams, which means I can simply say 1 mole of CO2 is 44.01 grams of CO2. Next, I need to go from moles to molecules. What is my conversion factor here? 1 mole of CO2 is Avogadro number. 6.02 times 10 raised to power 23 molecules. This time I'm doing molecules because CO2 is a molecule. That's it. You start now solving. 750 grams of CO2. Multiply it with a conversion factor that comes from this. This is grams, which means I put grams here so they can cancel. How many grams? 44.01. 1 mole goes on top. Next, I multiply with the second factor. Moles of CO2 I have, which is right here. So I multiply with the second factor. Moles of CO2 here, which means to cancel, I need mole of CO2 here. How many moles of CO2? 1. And 6.02 times 10 raised to about 23 molecules of CO2 on top. Mole of CO2 gone. I'm left with finally molecules of CO2. Now this is two significant figures. There is no decimal after this, which means this 0 is not significant. This is four significant figures. This we don't care because it's a fixed number. So my final answer should have two significant figures. When you plug this in, it will give you 1.0 times 10 raised to power 25 molecules of CO2. And that's it. That's your final answer. And that is how you basically convert grams to moles or moles to molecules or atoms. Everything is based on that particular map that we just saw. And we'll keep on building on that map for the next following chapters. So please make sure you understand this. You can practice more questions from the worksheets, but please make sure you understand this particular concept.